Welcome to this NPTEL lecture on techniques and principles of modern radar systems. We were discussing MTI filter, and today we will start with clutter, because that is the main motive for going to MTI filter, that MTI filter can remove clutter. We have already defined clutter, that clutter is the echo from a stationary target. It is of no interest to us, that means for a radar it is unwanted. Unwanted, but it will come because there will be various stationary targets. I gave an example that aircraft flying near an hill, or when the radar is looking and there is sea which has large amount of waves, ocean waves. So, that then wind, etc. So, unwanted things. Now, rain, then bird, hill, all this. Now, this is stationary, that means ideally we can say that ideally clutter, if we see the spectrum of the clutter, because in spectral domain the moving target and clutter can be easily separated ideally, because clutter will have a delta function at f is equal to 0, because it should not have any spread, it is in f it is 0. So, at 0 you can have a delta function. So, I can say ideally the clutter spectrum is a delta function at f is equal to 0. So, if I draw the spectrum, I will come there. Then, but in reality you will see that clutter has a not a delta function, it has a spread. Why? Because there is a limited relative motion with respect to radar. One thing is, as the example, that the wind. So, when suppose I am seeing the clutter from a hill, but that is coming through the wind. So, in the propagation path there is a motion of the wind. So, when the radar will get the echo from the hill, that will also have some motion. Also, the radar platform, that suppose the antenna is moving. So, the received signal that gets that scanning antenna, that will produce some a thing. So, wind, etc., as I said. Then in case of sea, there will be the waves. So, they have some motion. So, those motions are very small relative to the actual target's motion, but still it is not an delta function. That means, if in the frequency domain. Also, the clutter is random. So, we can model it with a random process, that sometimes I will see the clutter, always definitely I will see the clutter. So, it is a random process. So, that means its spectrum will be the power spectral density. So, ideally at this is the ideal A, if this is the 0 velocity delta function, but generally it will have a spread, or I should use some other color. So, small spread, and random processes we characterize by their that it may be 0 mean, but it is again moment that its standard deviation we will call it. So, first thing is it is a random process, clutter is a mathematically modeled as a random process. So, I can say that its PSD is concentrated. Obviously, the most of the power that is near the f is equal to 0. So, concentrated near f is equal to PSD is concentrated near f is equal to 0, and it is in the both sides of the frequencies, because there can be motions in either directions. So, this clutter process that is characterized by a second order characteristic, that is the its standard deviation, let us call it sigma f, and that is not 0. That is the crux of all this discussion, that it is ideally should have been sigma f should have been 0, but it is not 0. But obviously, this is small. I should also say that delta f is very smaller than the target speeds, or the I can say the FD of target, the Doppler of the target. Compared to that, it is much smaller, but it has something, and this is the sigma f is the overall speed, and generally it can be modeled as, suppose, sigma sorry it is the total overall spread, and this is the clutter spread due to platform motion, then clutter spread due to mechanical scanning of antenna, then clutter spread due to wind. So, I will say that this is the contribution of the wind velocity will make this clutter spread, then this is antenna motion. If it is a mechanical antenna, nowadays for phased array this term won't be there, then this is due to platform motion, then I can also say that the internal motion of the clutter, internal motion, etc. You can have various others. So, this overall, but this is small. So, I can say that this is the sigma f. Okay. Now, what happens if pulse radar actually is, you can consider a pulse radar that it is sampling the echo whatever it is getting, since it is sending repetitive pulses, we can say that it is sensing or sampling the returned signal at a frequency FR. So, after sampling, that means, since it is doing the pulse. So, if we see the overall spectrum, we can say that for pulse radar what will be the clutter PSD. So, I can say that clutter PSD due to pulse radar operation, or basically PRF type of operation. So, there this spectrum that will be not only, so this is F, this is my clutter PSD. So, this is 0, but at every FR this will be repeated, because a sampling operation type of thing is taking place. So, I can say again at 2 FR it will have these minus FR, minus 2 FR like that. So, we can say that in pulse radar the clutter PSD is concentrated around DC and also multiple integers of PRF. Now, this periodicity, so we can now if we want to remove it, then the problem is, since due to this spread, that means if in this zone, suppose this is a zone where targets echo spectrum also may be placed, and then generally the clutters are much stronger than echo in certain cases, and the whole radar pulse radar won't be able to see this thing. So, this is a problem for pulse radar. Now, what MTI filter does, it will have to remove this filter. So, I can say that what is the, suppose this is the thing. So, what now I can draw that what is a typical input, this is in F. So, what is the input given to the, so I have the MTI filter. So, the MTI filter, so I will say that, let us say this is the input and output. I should get this clutter removed by the MTI filter. So, what is a typical input to this MTI filter? This type of clutter. So, all same, maybe my drawing is, so at FR, 2 FR, also this is continue, this is minus FR, this is minus 2 FR, and also some of the targets will be there. Suppose I use this color, that let us say that there is a target here, there is a target, let us say here, there is another target here, let us say these 3 targets are there, and other places will be something like this. So, the signal is something like this, that means these are the signals. So, now I want finally to get only the green ones and not the blue ones, and obviously there will be noises etcetera. So, in this, that is why you will see that this noise floor, if we put a threshold, that can be easily removed. So, what is our desired this MTI filter response? I can draw that desired response, that means if I call this HF. So, desired HF, that I can say that we should try to have a null in the desired response. So, if I can have something like this, that means a null. Now, I am drawing this sinusoidal shape, it can be any shape, but I will try to put a very sharp null and some wide null, somewhat wide depending on the spread of the thing. Then, if this is the HF, this is the input. So, what will be the output? That means, MTI filter output. Now, I can draw that MTI filter output spectrum. So, what I will get? You see that these things will be all, the black ones will be removed with multiplication with this. So, I will finally get you see the targets. So, this is a desired thing. So, this says that what is desired of the MTI filter, desired HF of MTI filter is this. So, if I can get that, already you have seen that we have got something like that. So, okay. So, we will see that you see already the delay line canceller that we have discussed, that has this type of response. So, also I have mathematically derived that it is a pure sin pi f dt, that type of function. So, that can do this Doppler removal, but in the process you see that the blind speed etcetera has come. Now, we will discuss various MTI implementation of these MTI filters, and finally, we will compare them, because how much clutter is getting removed I am qualitatively saying, but we should require some figure of merit for that. That also we will see, there are 2-3 figure of merits, that how much clutter I am attenuating, how much MTI indicator that there is another very good performance matrix. So, those we will discuss then. So, next we will start with this implementation of MTI filter. So, implementation. One thing I have already done, the delay line canceller, but that I will now call single delay line canceller, because there is a single delay already we have seen that. Again just I am repeating for completeness sake that there is a delay of t and this thing goes in a summer and we get y t. So, this is the, this blue colored one is the single DLC and it has a transfer function that we are calling HT, impulse response that I am calling HT. The Fourier transform of that will be HF, its transfer function. Now, this is also called a 2 pulse canceller. Why 2 pulse? Because you see that its output will come after 2 distinct input pulses or distinct input echoes have come, because since you are delaying. So, this output is valid only after 2 echoes have come. So, a pulse, the phase detector output is coming either in the, you can make it either, if the processing is analog you can directly put it and there is a transmission line you can put and give it, or if it is digitized, as I have shown in the block diagram. You can put an AD converter, because now these frequencies are your after match filtering and phase detection. So, that is your IF frequencies, there AD conversion is possible. Nowadays, even at RF level also you can have AD, at least S band, etc. Even I think X band also you can have AD, whatever, but costly those things. So, this 2 pulse canceller. So, this requires 2 pulse, one is the direct pulse has come, then you require a delay. So, that means 2 PRIs are required, after that only you can take it. That means, after only a time of 2 PRI you can get it. So, this T we know is nothing but 1 by FR, and I can write the expression of YT. What is YT? XT minus X T minus T. So, I can write the impulse response, impulse response impulse response of the filter, that I will call HT. What will be HT? Simply we know del T minus delta T minus T. So, I can write its transfer function, steady state response, that will be, from here I know 1 minus e to the power minus j omega capital T, where what is omega? Omega is nothing but 2 pi into f, and in z domain I can also write the transfer function in z domain, because if these are digital circuits it is better to do it. So, we know that this can be written as, so this is Hz. Now, mainly what we interested, that how much attenuation it is giving, or power, how much power attenuation it is giving. So, I can easily find out what is the power gain of this, power gain of MTI filter. So, that we know power gain will be H omega square, and since H omega is complex, so H omega star, and so that means it is 1 minus e to the power minus j omega t into 1 minus e to the power j omega t. So, this you know 1 minus e to the power minus j omega t plus e to the power j omega t plus 1. So, it is 2 1 minus cos omega t, and that is 4 sin square omega t by 2. So, power wise it is a sin square thing. So, if I draw that in the amplitude response of the filter, magnitude response or amplitude, I should say magnitude response, MTI filter. So, you know the maximum value can be 1, and this side is, let me take it f by fr. So, at 0 it is this, at 1, at 2, at 3, etc. So, I know this is a sine square graph. So, if I plot it, so this will be the magnitude response in volts. The power relation will be square of these, and typically this magnitude response is also plotted in the dB scale. So, we can do that magnitude response versus F by Fr. So, this is 0, 1, 2, 3, and we know that this value will be 0. So, this is typically given in dB, 0 dB, and the graph you will see so this value are typically the 10-20 dB. Now, that may not be always very good. So, we can summarize what we have got from single DLC, that the peak occurs at f is equal to 2n plus 1 by 2 Fr. You will see this is the peak, and null occurs at f is equal to n Fr. So, this part is okay, that null is occurring at n parallel to f is equal to n Fr. So, then you are removing clutter, but what happens that it is having a peak here, and in other portion there is a attenuation of the other Doppler velocities, Doppler frequencies. So, that means some of the velocity targets they will be attenuated compared to this peak. So, we can say that what is the problem in many, actually in other applications this type of response is not acceptable. So, we can say that unacceptable performance from single DLC. Actually, what we want? We want that this thing should be something like this. Ideally, I should have something here, and at 1 it should go there, then everywhere it is uniformly. So, that all the target speeds they are given correctly at that position, at integral multiples of Fr there should be a 0 position. So, that should have been the ideal one, but it is not ideal, it is having a severe attenuation. So, in filter unacceptable for radar applications. So, single DLC is unacceptable, we will have to better the performance, And what is our problems? That stop band notch is not wide. What do we mean by this? You see that this notch, this is the stop band notch. You see near stop band, if it had been wider, more and more clutter will get removed depending on the I think actually in practical radars the clutter spectrum spread, the delta f is 5-6 Hz. Now, if you do not have this 5-6 Hz this notch width, then some of the clutter will leak through. So, it is not having that, stop band notch is not wide. And second point is pass band response is not uniform. So, targets, the we know due to this the targets will get non-uniformly attenuated. So, these are the two problems that we will have to, I think this writing is not clear. Notch. So, we need to have much wider stop band notch, at least to the spread of the overall spread of the Doppler spectrum, and pass band response we should be more uniform making. So, that is not possible by single DLC. So, this I will say that single DLC or SDLC. So, we will see that how to make improvement of that in the next class. Thank you.